The mathematical expression for the first law of thermodynamics, or the energy equation, includes a term which accounts for any work performed on or by the system during a process. One common form of work done in piston-cylinder devices is called moving boundary work, or simply boundary work. Consider a cylindrical vessel containing a fixed amount of some substance. A piston is placed in the cylinder on top of the substance. Let's take the substance as our system. Moving boundary work occurs when the boundary of the system moves as the substance is expanded or compressed. We will now derive a mathematical expression which we can use to calculate boundary work. Consider the gas enclosed in the piston-cylinder device. The gas has an initial pressure P and a total volume V. The gas expands and the piston is allowed to move a differential distance ds. The differential boundary work done during this process is equal to the force on the piston times the distance the piston is moved. The force acting against the piston is equal to the pressure of the gas times the cross-sectional area of the piston. The product of this area and the distance the piston moves is equal to the differential change in the total volume of the gas. The total boundary work done as the piston moves from point 1 to point 2 can be obtained by adding all of the differential work from state 1 to state 2. This is done by integration. Recall that work is a path function, so the integral of the differential boundary work done from point 1 to point 2 is simply equal to the total boundary work done during the process. In order to integrate the right side of the equation, we need to have a functional relationship between the pressure and the volume. In other words, we need to know how the pressure changes as the volume changes. This functional relationship can be seen by plotting the pressure as a function of the volume. Let's look at some examples of different process paths on the PV diagram. Suppose that the initial pressure is P1 and the initial volume is V1. The simplest case occurs when the pressure stays constant as the volume changes. In this case, the process path is simply a straight line from the initial volume to the final volume. Because the pressure is constant, it can come out of the integral. Evaluating the integral tells us that the boundary work done during this process is simply equal to the pressure times the change in the volume. Note that the boundary work is equal to the area under the process path on the PV diagram. Now, let's look at a different case where the gas behaves as an ideal gas and the temperature of the gas remains constant during the expansion process. The ideal gas law provides the functional relationship between pressure and volume. This relationship can be shown as a process path on the PV diagram. The mass of the system, the gas constant, and the temperature all remain constant during the expansion process, so they can come out of the integral. Evaluating the integral provides us with an equation for the total boundary work performed during the process. Again, the boundary work is equal to the area under the process path curve on the PV diagram. It's important to note that the equation we derived for moving boundary work is for a quasi-equilibrium process. This means that the system remains nearly in equilibrium at all times. In other words, the process is sufficiently slow that the properties in one part of the system do not change any faster than those in other parts of the system. For example, the entire substance in the piston-cylinder device is at the same pressure at any given time. A quasi-equilibrium process is an idealized process which can serve as a standard to which actual processes can be compared.